You're on mute, Brandon, you're on mute.
Well, thanks, Gary. You think after 5 years of doing this, I would at least get that part of it right. But every now and then we all make a little mistake here. Brandon Garrett here with the National Minority Quality Forum. Thank you all for joining us. I see the participant numbers are going up and up. That's because I guess you all have an interest in today's topic. What does astrobiology have to do with healthcare policy? Now, that's something that I never thought we'd be talking about here at NMQF on one of the Friday webinars, but have a bit of interest in it myself. But before we delve into that topic a bit with Dr. Pucker and Dr. Wong, I just want to make sure that when I take care of some housekeeping things, one, if you have a question that you want to ask of either doctor, please just use the Q&A box and answer it. I mean, place it there and they'll get to it. And then two, if you have a comment or something you want to make others in the group aware of, please use the chat function and put it there. Finally, I just have to do a quick plug for NMQF. We have our depends on who you talk to. It's either the 23rd or the 22nd annual summit on health disparities that's going to take place in Washington, D.C. at the Conrad Hotel, April 28th and 29th during National Minority Health Month, which is a month that Dr. Puckrin started. And then two, at the end, at that event, we honor our top 40 under 40 leaders in healthcare. So if you know a minority health leader that you that would like to that should apply, please have them apply. And I'll put links to both the registration and to the 40 under 40 application in the process. Without further ado, you guys all know him. He founded uh actually I remember the Institute to Find Minority Health Month in 1998 and eventually trained into the National Minority Quality Forum. He has a doctor, he has a paper doctor, as Dr. Robin Kelly always says. He has a PhD in history, but he also in that study of history studied how things happened, how people survived and died and lived well. And so with that, he started NMQF. And without further ado, I'd like to turn it over to Dr. Gary Pucker.
Good afternoon, everyone, and thank you for coming and participating. I can't tell you how excited I am about today's conversation. I live in Washington, so I attend a lot of policy discussions about healthcare, and it always dissolves into a conversation about money and less a conversation about uh, how do we conserve life and how do we make sure that everyone has that access to best modern therapy. And I'm really pleased today to change the script a little bit and begin talking about it against what are the natural laws of science that sort of dictate how our bodies operate. And I want to introduce you to Dr. Michael Wong. He's an astrobiologist. He's written some fascinating papers that we'll have a chance to talk about today. But I thought we'd start off by asking Dr. Wong to introduce himself and tell a little bit about how did you get to astrobiology?
Yeah, thanks so much, Dr. Pucker. And it's a real pleasure and an honor to be here speaking with you all. And I also never expected to be a part of a seminar about astrobiology and healthcare, but here we are nonetheless. And I think a little bit about my background. I'm a planetary scientist by training. I grew up inspired by a heavy dose of science fiction as a kid, and always thought that like the greatest job in the world would be to think about life elsewhere. Can we find life beyond Earth and explore outer space and understand our place in the cosmos? But as I, grew into a professional astrobiologist, I began getting a little bit worried that all of my energy and talents were going toward this sort of like far off esoteric goal that had nothing to do with the well-being of anybody here on Earth. And so with a little bit of motivation and creative thinking and excellent colleagues who also liked thinking about the connections between looking out at the cosmos and looking in at ourselves, I was able to write a few papers in the past few years that try to bridge that connection between what I do as a space scientist and what you all care about here, which is the well-being of people on Earth. And one of the questions that I always get asked as an astrobiologist is, how can you even do astrobiology when you haven't discovered life in space yet? Which is absolutely a fair question, because it's true, we don't have definitive evidence of life beyond Earth yet. But I like to answer the question by kind of surprising people and telling them, but wait, we actually do know of life in space. And then, their eyes widen, their jaws drop, and they wait with bated breath for me to reveal some government secret about where we're keeping the aliens. But then I just remind them, you're life in space. I'm life in space. We're all life in space, right? The moment we discovered that our entire biosphere existed on the crust of this regular rocky planet orbiting a very normal star, one of 200 billion stars in our galaxy, which is one of a trillion galaxies in the universe, we discovered life in space. We discovered that we are life in space. And the exciting question that astrobiologists get to try to ask now is there more life in space out there? And I think that there are actually some very subtle connections, but important connections between that question and how do we preserve and protect the life that we have here on our own planet.
Great. So I'm going to assume that lots of those who are listening to us, including myself, don't have a physics background and don't understand some of the language and some of sort of the rules of the road. So I want to start off by asking the simple question of the universe being homogeneous and isotropic. If you could sort of start us there, I think that would be a good place to begin.
Okay, yeah. So, as if anybody's a fan of the Big Bang Theory TV show, right? The theme song starts out with the universe started in a hot, dense state, and then so forth and so on. So it's true that our universe started off in what we call a very low entropy state. As Dr. Puckeren mentioned, homogeneous, which is like, it's the same everywhere. It was extremely hot. Nothing complex or interesting really could have formed in the first few seconds of the universe's existence. But over time, the universe expanded, cooled down such that atoms and molecules could start forming, and then stars formed, which lit the heavens and forged yet more complex atoms and isotopes. And eventually, after the first explosions of those first stars, that spread about this cosmic stardust, which Carl Sagan reminded us that we are all made of, and this cosmic stardust eventually coalesced into planets, and some planets eventually, at least one, our Earth, spawned life. And so we really are connected to the cosmos and its very beginnings, even though it started off in a homogeneous isotropic state. Thanks to the laws of physics that we enjoy in our universe, it was actually able to generate a lot of creativity out of that bland, hot soup. And one of those things happens to be us.
And so part of that is that the laws of physics, the laws of nature are the same throughout the universe. Wherever you go in the universe, the laws are absolutely the same. Is that a fair sort of characterization of it?
Yeah, as far as we can tell, the laws of physics are the same everywhere in the universe. That is to say, if you do a scientific experiment here on Earth, you should be able to, do that kind of experiment somewhere else and use the laws of physics to correctly predict, whether you're doing an experiment on Earth or on Mars or on Pluto or somewhere, even farther than that. The same laws of physics should be able to correctly predict the results of that experiment. So a very simple experiment, for instance, would just be to throw something up in the air and then catch it, right? So I just threw my USB stick up in the air. I predicted where it was going to land. My brain moved my hands to the right place and I caught it. Right. And so, if you go to Mars, which has, a lower gravity than Earth's, so the experiment's going to wind up different, right? I'm going to be able to throw that USB stick farther, but the laws of physics you will be able to use this exact same equations. You just plug in a different gravitational constant, into that equation, and then I will be able to predict I needed to move my hand so much further away to be able to catch that object in motion, right? And so that's what we mean by the laws of physics are the same. It doesn't mean that everything is going to be the same. Like Mars is a different planet from Earth. Importantly, it has a different amount of gravity, but the underlying universal principles governing what happens are the same, and you can do the same type of experiments on Mars.
So when it comes to life, and let's take human life, those laws of physics apply to every human being on planet Earth as well, right? There's no exception, there's no scapegoat, there's no hatch that makes a difference from anybody.
That's right. We are, physical phenomena. We are embedded in the universe. As we've already mentioned, we are star stuff, but we are also planet stuff, right? The origin of life happened on Earth some 3.8 plus billion years ago. It was a single-celled organism that was subjected to the same laws of physics as everything else. And through the marvelous wonders of evolution over deep time, life differentiated and grew in complexity all the way to us. But there's still nothing that separates us from the rest of the material world. We are a product of our universe's creations and of our planet's creations, and we have evolved in response to the physical and chemical conditions of the Earth. So we're very much embedded in the physical universe, and that means that we can begin to use the principles of physics to understand how life works. So you may have heard of the subfield biophysics, which deals with like how do you describe the underpinnings of biology using physical principles. So for instance, people have thought about like the structure of DNA, right? And you can appreciate that as a sort of like ordered crystal, the way that you can try to understand non-living things through the same types of techniques. If you wanted to study, say, the molecular makeup of minerals, for instance, it's not too dissimilar to try to understand the molecular makeup of our DNA, the code of life. Other physicists have discovered certain laws of life that describe regularities in, say, how fractal like our blood vessels are to be able to transport nutrients around our bodies. And it turns out that that fractal like nature is found all across the animal kingdom, and indeed, if you look to plants too, and the trees that are outside my window, they look like fractals as well for very similar reasons.
So Edwin Schrödinger in 1943, bringing up DNA, was interested in understanding how hereditary material was passed along from one generation to another. And he essentially speculated that there was something chemical going on that explained that transfer. And then Crick and Watson sort of picked up that idea and sort of helped to the discovery of DNA. Schrödinger gave a lecture in '43 that sort of made those points that then became a book called What is Life? But one of the things that really strikes me about what he had to say that I think is so foundational was that not only was life emergent from from this chemistry, but there was a need to be adherent to the physical laws, to a certain orderliness, that it wasn't random, that there was this orderliness that is associated with life, and that orderliness was associated with the fundamentals of physics. And I think I'm saying that correctly, that there is an
Yes.
order to it.
That's right. That's right. And in Schrodinger's lectures and subsequent book, What is Life, he wrote about this in terms of what he called neg entropy. So for those of you who aren't familiar with the term entropy, let me try to explain that first. Colloquially, entropy is just a measure of the amount of disorder in a system. And there's a famous law of physics, the second law of thermodynamics, which states that over time, the entropy of any closed system should be increasing over time. And I think we see this all the time in our daily lives. Entropy explains why you can crack an egg, scramble it, and fry it, but you can't unfry, unscramble, and then put the egg back in its shell and make it look perfectly ordered again, right? So there's some kind of like arrow of time that describes this increase in entropy in ordinary non-living systems, from the way that, we cook things to the way that, our rooms just naturally get messier over time until we put in the work and effort to clean them up and, order our closets, right? And so the second law describes so much of our regular world, but not quite life. Schrodinger says there's something weird about life, and he said it is neg entropy that's happening. And so neg entropy is like the opposite of entropy, which is that instead of things getting messier and more disordered with time, life appears to be getting more ordered. And there's one way of looking at this, which is absolutely, yeah, like, think about all of the molecules that make up who you are. And you think about, you know, you might think of yourself as a total mess, and sometimes I think of myself that way. But honestly, we're so perfectly ordered in that if you scrambled a little bit of who I am, I'm not going to function very well, after that. Whereas if you took, like, say a rock, right, which is not alive, and you scrambled its molecules, you took a little bit of the rock and you put it over there, and you took this little bit and put it over here, it's still going to be a rock at the end of the day, right? You can mix up the molecules inside of a rock any which way, and it will still be a rock. But if took my eyeball and put it on my foot, it, it's a recipe for disaster. And especially if you start tinkering with my DNA, right, which are tiny molecules. But if you scrambled that information in there, my body completely loses its functionality, right? And I guess that ties into some of what happens in diseases and cancers, which we may touch upon later on. But to Schrodinger, life was this perfect example of neg entropy, that we're so ordered to the degree that what life has to be able to do is drink in neg entropy from the environment. Now, very importantly, life does not defy the second law of thermodynamics. The second law of thermodynamics, which says the overall entropy needs to increase with time, is still valid. So in order to resolve the conundrum of how life maintains its orderliness, if it's drinking in neg entropy, it must at the same time be producing tons and tons of entropy outside of itself, right? So that means that life needs to basically produce exhaust that it dumps into its environment to pay its dues to the second law of thermodynamics to maintain its own internal complexity. And we see this also all the time. In order to run our cars and factories, we have to dump a lot of excess waste, heat, and exhaust into the environment. In terms of our own metabolisms, you're constantly breathing things in and breathing things out. You have to continue to exhale and also inhale, right? So you have to do both, right? The exhalation is you raising the entropy of your environment. There's an old joke in astrobiology that oftentimes, because the way we look for life on other worlds is to try to spot its exhalations, the things that it's producing and impacting its environment with, we like to remind ourselves, no shit, no life. Right? It's just like that's kind of like life is one of those entropy producing engines, and it has to do that because the second law of thermodynamics says it has to do it in order to maintain its own low entropy, what Schrodinger called neg entropy. Hope that made sense. I know it was a complicated story, but that's really what's happening with life.
And also it is that orderliness that is associated with it. So when we start to look at something like healthcare, right? So what healthcare is essentially trying to do is to maintain that order. What we call disease, at least Gary Pucker sometimes thinks about it as disorder in the cellular functions of the body. And what medicine is trying to do is to restore that order to the best that science will allow us to do. And in order to do that, it has to follow those physical laws. It can't make it up. And that's where the clinical trials and the research and all of the studying that people do to understand that the precise nature of that orderliness to make a difference. Is that a fair sort of characterization of what it is we're trying to do?
Yeah, absolutely. Right. So one thing that is important to appreciate is that life as a phenomenon that can be expressed at many, many different scales, from the tiniest bacterium up to a human being. And then also, I think fairly, you can describe an ecosystem as a living system. You can describe human societies as living systems. Some people even go so far to say that, there are very strong analogies to our technological systems in the way that they evolve. I've seen people draw basically trees of life the way that you might draw a family tree, but for like large language models, the chat GPTs of the world, right? These things are also co-evolving with us. So we should be able to see the principles and the laws of life at all of these different scales. And so the healthcare system is one of those systems that is composed of smaller parts that we would normally think of alive, human beings. But then, you can always just say, oh, look, a human being is composed of smaller things that are also alive, our cells and our gut microbiome. And so there's no reason, I think, why you can't describe some of the healthcare system as a whole, as a unit, as sort of like a living being. And so if the healthcare system embedded within our society is trying to perform a function of maintaining negentropy, maintaining orderliness, maintaining a functional state, then it absolutely can be described in some of the abstract terms that we've been talking about to describe all living systems. And then the question is, what can we do to basically promote the functioning of our healthcare system?
And so let me give a little background now. This is sort of Gary Puckrid's sort of look at our healthcare system as it functions right now. There's an underlying assumption to it that we can't provide quality care to everyone. And so our healthcare system has a rationing component to it. And there are lots of mechanisms inside the system when you take a look at it. And many of the patient advocates and policymakers on the call will know exactly what I'm talking about. Value-based purchasing, CBO's Congressional Budget Office scoring, all of these are sort of financial risk mitigation systems, but they're not necessarily aligned with those physical laws of nature, right? And so when they get misaligned and they're not helping the cells, the body, the biology back to that orderliness, what we witness is the hospitalizations, the emergency room visits, the disability, the elevated mortality, which is not to say that the science will allow us to avoid all of that, but the disproportionate consequence on certain populations is a function of the way in which our healthcare policy system. So the example would be, there's a medication that we know you need, but our healthcare system would say, well, we'd like you to fail on this other medication that is not as effective, but is cheaper, and we'd like you to fail on that before you give you what you need. But in that instance, we're allowing disease progression to occur, or we're allowing those hospitalizations and ER visits. And so that orderliness, you can't avoid it in our healthcare system if you are actually going to optimize the delivery of care. And that's why I think the work that you do in astrobiology, the science and the physics, really have important lessons for healthcare. That at the end of the day, we all, whether we're on planet Earth or when you get the Titan moons or Saturn moons, etc. If you find life there, it's going to have that orderliness about it in order to be sustainable, I would think.
Yeah, that's right. So one of the foundational sort of functional pillars of life, no matter where it is in the universe, here on Earth or in Saturn's moon Titan, if life there does exist, will be homeostasis, the ability to respond to both external and internal fluctuations and perturbations and be able to maintain certain important set points so that you can persist. And honestly, it all boils down to persistence for me. That which persists exists, right? If you're able to maintain yourself, you will see yourself, march through time and still be around. And that is what life has sort of, been able to do. That was one of the first, I guess, tricks that life learned when it was just emerging from a chemical soup into the first living organism was, how do I maintain myself in the face of a very complex and dangerous world? And it figured that out on the chemical scale. And then as life continued to evolve and complexify and grow in scale, it was able to figure out how to do that at macroscopic levels as well. And now that life is a planetary phenomenon, right? There's very little of planet Earth that hasn't been touched by or influenced by or even inhabited by some form of life or another. And life really has embedded itself into global cycles. One great example of how life has transformed Earth at the global scale is by injecting oxygen into our atmosphere, right? We owe the presence of about 21% oxygen in Earth's atmosphere to photosynthetic life, which breaks apart water using sunlight and throws the oxygen into the air. And then we evolved to be able to take advantage of that oxygen. It's really a story of coevolution with planet Earth, and I think that the a perspective from astrobiology of looking at life through deep time and understanding how it co-evolves with its planet to enable planet Earth to sustain life further into the future, this kind of homeostasis, this feedback, not just between life and itself, but life in its environment, that they are co-creators of planet Earth, is really profound. It helps us obviously try to look for life elsewhere because we can kind of predict what signals and environmental factors we need to look for to find life on, XYZ distant worlds. But I think it also makes us reflect upon our own place on planet Earth, that we have at once a lot of power to influence our environment, and we are doing that, but also that what goes around comes around, right? That because we are so intertwined and embedded within our Earth system, when we perturb our environment, that environment will then come back and influence us, and we will both change. We will co-evolve.
Yeah, and so the planet figured out a way to get oxygen, and we're figuring out a way how to get carbon dioxide into the atmosphere. So, and that obviously we're talking about climate change. So let's talk about Fermi's paradox for a second.
Sure.
So why don't you tell a little bit about Fermi's paradox, because that informs some of the work that you do and what you're thinking about, and then we'll sort of bring that back to healthcare.
Okay. So in astrobiology, there is this paradox, which is basically the simple question, where are all the aliens? Right. And so this was a question that Enrico Fermi, who was a physicist many decades ago, asked casually at lunch. And so hence the question has been named after him. So the idea behind the paradox is a paradox because it seems like the universe is very amenable to the emergence of life, right? It seems like, as we were discovering increasingly, the building blocks of life are everywhere in the universe. The recipes for chemical complexity, you can find them on meteorites and asteroids and comets and all sorts of moons in the outer solar system. And there's no reason to believe that, we should be alone given all the generative, creative power of the universe, and yet we haven't found anybody. In fact, nobody's come to visit us yet. And so the Fermi paradox is like, so where is everyone? Why do we hear this great cosmic silence? And so there have been many proposals for why we can't, why aliens haven't truly visited us yet, or why we haven't found little green men on Mars. Maybe there's some kind of bottleneck on the way to evolving the way that we are. Maybe it's very unlikely that you get, say, animal life or complex cells or something like that. That would make it very difficult for there to be another civilization out there that we would be able to make contact with. Other people speculate that, the bottleneck is in front of us, not behind us on the evolutionary timeline. Maybe it's that when we get to where we are, most civilizations destroy themselves. Maybe people have talked about, nuclear war, or pandemics, or whatever, these types of things. Climate change, of course, another one that is sort of an existential threat to our civilization. And so one way that you can reconceptualize the Fermi paradox for me is by looking again back at evolutionary history and the giant leaps in complexity and understanding and information processing capabilities of life throughout that evolutionary history. And you start to wonder, okay, back when life was just some bacteria, like some slime on a rock in the ocean, could it have used its abilities to predict the next stage of evolution? Probably not. Back when life was just unicellular eukaryotes, and you can ask the same question. Could slime molds have predicted ant colonies? Could ant colonies have predicted human civilization? And you think, so if those things couldn't have predicted next leaps in evolution, what can we not predict yet about what we're going to become next? And so maybe we can rephrase the Fermi paradox, not where is everyone else in the universe, but what is everyone else in the universe now, right? What have they evolved into? And one tantalizing possibility is that they don't evolve into great galactic empires like in Star Wars that goes around and conquers all these different planets and basically does, colonialism. That's such a naive hypothesis because it's taking what has happened in, say, the past 400, 500 years of human history and simply linearly extrapolating what that's going to look like into the cosmos and saying, oh, yeah, just because humans did that in the past couple hundred years, that's what any civilization is just going to do forever, just expand into the cosmos and conquer things. And maybe that's not what a truly intelligent civilization does. Maybe instead of taking that kind of colonialistic, extractivistic point of view, a civilization that is truly enlightened will realize, wait a minute, what we've got to do is figure out a way to live in harmony with our own planet. This is the place where we make our stand. This is the place that we need to perfect. And they start growing in dimensions that are different from just mere spatial expansion into the cosmos, colonizing neighboring planets, and then eventually perhaps even neighboring galaxies, and say, wait a minute, what if we, again, getting back to the main point of homeostasis and orderliness, fixed all the problems here at home first, and it became a civilization that really prioritized that. And one of the open questions, I think, in astrobiology in general is like, what is life optimizing for? And this can be asked of the healthcare system as well. What is the healthcare system optimizing for? Is it optimizing for, profit and patient throughput and this sort of capitalistic engine? Or should it be optimizing for something else, which is like the well-being of our society? And what would that look like? What would the results of that look like? But I'm not an expert in the healthcare system. That's for all of you to ponder. For me, in my work, what I think about is, okay, what would the signs of life look like for a planet that has discovered that it should reprioritize its optimization function, not for infinite expansion into the universe, but for trying to maintain that homeostasis at a planetary scale? And so that's sort of where my astrobiology work goes in. But I think it also has implications for what should we do as a civilization? And the last thing that I'll mention here is that I think it will take a very long time for us to discover signs of alien life elsewhere. It could be a project that takes hundreds, if not thousands of years. And then to actually have a meaningful conversation with these aliens once we do find them could take thousands of years more. And so I really do think that in order to give ourselves the best chances of discovering and communicating with alien life elsewhere in the universe, we literally have to become the thing that we're looking for, right? We have to become a long-lived civilization that has figured out a way to persist on its dynamic, changing planet for a long time. And so we have to literally become the hope that we're looking for. And I think that that's the way in which astrobiology really makes us reflect on who we are and where we need to go next.
Now, one of the things that certainly we think about, and certainly myself included in that, is that there are these fundamental laws. They operate independent of us. We can learn about them. We can influence them. We can build around them. I'm not sure we'll ever figure out how to change them from what they do, but maybe some science out there will sort that out one of these days. But the point is that when it comes to sustaining our populations, when it comes to delivering healthcare, when it comes to making sure that every American lives a very high quality, long life, and to your point, um, how do we conserve life more generally? Um, uh, we have to be mindful of those physical laws. And certainly, uh, here in Washington, we interact with members of Congress and the executive branch and down at the state level. They don't know anything about those laws. They don't take them into account. They operate as if um, they're the arbiters. They have the uh, somebody's given them the pen and they can write the rules and regulations. Um, uh, and but along the way ignore the fact of that, as you suggest, the environment pushes back, that there are consequences to be paid here. And so really the challenge is in the short run, and you think about the context in which I'm saying this, meaning the current context in which I'm saying this, is that we have to figure out how we align ourselves with those laws that actually made us, and how do we build our healthcare system so that it is um, part of that living process that is connected to our biology and trying to optimize. The shorthand that sometimes I use when I think about your question, what is the healthcare system doing? It should keep us out of the hospital, keep us out of the emergency room, keep us from disability, keep us from dying to the extent it can, and giving us high quality, long lives. And in order to do that, there's an orderliness to that process. It's not random. It is an orderliness, and that orderliness has profound implications for the way in which we structure our society, put the logistics together in order to deliver healthcare. And I would say, too, when I think about the Fermi paradox, I think we have a responsibility to conserve life. I mean, uh, maybe there's other things, life forms out there, and maybe not. But for the foreseeable future, we're it. And it took a lot of years for us 3 billion years for us to get to this place. And I think we owe an obligation to the generations in front of us to build a system. One of the things that I'm paying a lot of attention to is the work that's going on in cancer. We are getting close to controlling cancer. Um, you know, the early detection work that's going on, the immune therapy that's going on. But yet and still what we see is that certain populations don't have access to that technology. And it's by design. The system is designed to do that, to differentiate of who has access to high quality care and who does not. And I think that's the solution that we have to address, because you're absolutely right. We need to get in harmony with the environment that sustains us and be able to pass on to generations a world in which they can continue that search for aliens and exploration or whatever else comes in front of us. But I think that is the deepest challenge, and it's a policy challenge. It's a collective will challenge. It's not necessarily a science challenge, because the science is, we are getting really smart, and I think there's such a large opportunity here for us.
Yeah, I couldn't agree more. I couldn't agree more. And I think that, what we need to make sure that we do is be able to understand these laws of nature that influence us, and be able to have the courage to choose when there is a conflict between laws that dictate short-term gain. I'm sure folks in Washington who hold this kind of power, they do understand certain laws, and I'm pretty sure those are, say, economic laws. They know that if they do this a certain way, they can maintain certain profits and keep the economy growing and things like that. But we have to also be able to recognize that there are laws that exert changes over long time scales. And these are some of the laws that, nature abides by. And one of those, to just bring things back to climate change, is just the way that, the radiation from the sun and the greenhouse gases impacts the release of heat from our planet. And there is a tension, right, between the laws that govern how our economy will grow in the short term and the laws that govern how the temperature of the earth will grow in the long term. And we have to have the courage to understand both of those laws and to be able, for the good of the future generations, exactly as you said, Dr. Pucker, and to choose to prioritize the functioning of our society in accordance with knowing that in the long run, we are really damaging the habitability of our planet. While in the meantime, providing for all of the people that currently exist on planet Earth.
So the conversation that you and I are having, and maybe I'm wrong, but I don't think there are a lot of physicists who would say anything that we've said here is inaccurate, in the sense that there are these physical laws out there. They operate. They're the same throughout the universe. They're apparent in the way our bodies work. That if we want to maintain well-being individually or collectively, that these laws are there. That we have to learn how to understand them and use them. Why is that so hard to communicate? I mean, you guys have known this. It's got to be, if we go back to Schrodinger, I think the whole quantum revolution is over almost 100 years. I mean, this is not like new stuff that we're talking about, but it seems to be locked in spaces where the general public is not getting access to it, that our elected officials, they're strutting around, but they don't kind of understand it or try to apply it. So help me understand, from the land of physics, where you guys, I mean, this is kind of commonplace. I mean, they would look at it and say, well, that's not new stuff. We want to do new stuff. What's the breakdown? How do we fix this?
Yeah. Okay. So I see maybe three things at play here. The first is that science communication and scientific journalism and scientific literacy just need to, grow, right? And honestly, most scientists are really terrible at communicating their ideas to the general public, especially to politicians. And there's often not a very good avenue to even do that. I mean, we all say you should call your congressperson, but then, if you just spout like equations after equation after equation to them, it's not going to work, right? So there is an art and a science to being able to translate this well-founded scientific knowledge to the general public. The next roadblock, I think, is in complexity, which is that, okay, physicists like to deal with very simple systems that we can wrap our minds around, that deal with, a particle bumping into another particle or something like that, or the way that light will bounce off and be absorbed by a certain molecule. And human life, human society is the quintessential complex system. There's so many different forces at play, so many different kinds of motivations, and it's messy. And so there's a roadblock in terms of translating what a simple lawful statement from physics has to say to like how human societies should operate, because there's a huge leap in complexity there. I think that's unsolved. And then the last thing that I will say, which is maybe one of the reasons why we haven't fully embraced all of these laws yet, is because we're still in the process of discovering new laws of physics, especially those relating to how life functions. What are the universal laws of life? That is still a question that people are wrestling with. And we've discovered lots of laws of motion, how balls fly through the air and bounce and things like that. Those are set in stone. But what the principles are behind how living systems operate, especially how they emerge, is still physics that has yet to be, I think, fully described or at least fully accepted in the scientific community. And Schrodinger even wrote about this all the way back in 1943. He mentioned that the principles governing life, in order to understand them, may require new physics to be developed. And so I think that the discovery, the invention of that new physics is still a project that is underway in science today to truly understand all of the laws that govern life. And again, because life is so complex and human societies are yet more complex, it may still be, in the future, the development of those laws.
So at NMQF, we are wrestling with this, and the wrestling part of it, to your point, is a conversation with a lot of different audiences who receive information differently and act upon it differently. The example I would give is, because it happens, we have courts, and courts decide the science. It's not that they understand the science, but they philosophize about it, because I think not even necessarily call it a conjecture that they have, they just philosophize about it. And so you have to treat each one of these audiences very, very differently, with all of the complexity that you described. Physicists love math. I mean, they would say, well, we can't do anything until we have an equation that allows us to analyze it. But when I go down into the community, I can't take an equation with me. I can't, it will not compute. And so the repurposing and finding the correct language to use is part of the challenge that we have right now. If you notice in this conversation, I didn't say to you, talk about functional information, which I know is critically important to the work that you're doing, but it would take us a while to take this audience through that. And so we have to figure out a way in which we can interpret and make accessible, because in a democracy, everybody gets to vote, and they need to have that sort of information in front of us. And that's the challenge. So, I think the work that we're taking on right now is getting our healthcare policy and financing system to accept the fact that there are physical laws out there that you can't control, that when you make a decision that misaligns with those laws, you are going to bring structurally inequities into the system. You are going to bring disorder into the system, and it's going to manifest itself in hospitalizations and mortality and disability and poor quality of life. That's a huge, almost multi-generational effort because our healthcare system was not founded on that. The science was, the DNA that we've learned, the CRISPR, all of that wonderful technology is all founded on that. But when it comes to healthcare policy, it's not necessarily built around that. Andrew, are you joining us or no?
No, I think I clicked on the wrong link. Sorry.
Okay. Andrew is our communications person. Great. But in any case, that's sort of the work of NNQF and what we're trying to do. And this is why your work is so fundamentally important to us, because I think what you're trying to introduce from the work that you're doing in astrobiology to bringing it back to planet Earth and saying, so here's what I see out there in the universe, and what is the implications for the way we're doing things on planet Earth.
That's right. That's exactly right. I see a question in the Q&A.
Okay.
Should we take that?
Yeah, please, let's do that.
All right. So an anonymous attendee asks about putting people on Mars, which is certainly not an inexpensive endeavor. So as a science communicator, how might I advise health advocates to perhaps encourage the administration to redirect such investments into important Earth-based science that could benefit people here and now? I think this is more about learning to speak Trumpese than it is about making a scientific argument. Yes. Okay. Well, I am not an expert in speaking Trumpese, so I am just going to make the scientific argument, which is that putting people on Mars, I mean, the whole idea that we can go to Mars and thrive is so problematic, especially if you put it and you weigh it at the same time with the idea that, we could pour effort into. Okay, well, I think the dichotomy that I just want to strike here is between what people call terraforming Mars, turning it into a place that we could send astronauts, perhaps even a whole society, and where they could thrive, versus taking care of our own planet. We already have like a 99% functioning planet right now. We are damaging our ecosystems and destroying biodiversity. But despite all of that, planet Earth maintains largely, functional, way more functional than Mars is right now in terms of, supporting life, especially human life as we know it. And so, it would be way more difficult, like 1 trillion times more difficult to go to Mars and turn it into Earth than to just try to repair what we've damaged here on Earth. And so I feel like trying to understand that, because I think one of the main motivations for going to Mars is, we're going to save the human species, right? We're going to it will be important for the long-term survival of our species. When if you really cared about prolonging human life into the future, why not focus on raising the persistence of where all the humans live right now, right? I feel like that is the main scientific argument, that because we are so reliant on our environment and the coevolution with that environment, in order to get somebody to survive on Mars, you'd have to bring that environment with them. And seeding that environment on Mars is going to be so much more difficult than repairing it on Earth. And then also, you also want to think about the intrinsic value of Mars itself. Mars is a completely separate world with its own history and story, and maybe even indigenous Martian life that we haven't discovered yet. And if so, then there's a huge amount of moral and ethical value in perhaps just letting Mars be, right? Rather than going there and disrupting it for our own purposes. But we could learn a lot from Mars, studying it scientifically. But if we go there and tromp all over it and ruin it, that kind of value might be gone. So that's another kind of secondary avenue there. But I think that the main one is that, let's take care of the home that we have here first before trying to make a brand new home in a very inhospitable environment.
Yeah. So, I just want to pick up on what you said, and unfortunately, Dr. Wong is going to leave us in about a minute, and then I'm going to finish up the thought after that. Yeah, first, let me say this. I want to thank you for agreeing to come and speak with us today. Incredibly important. This is not the average conversation that goes on in Washington as it relates to healthcare, even though the work that you're doing is so profoundly important to the work that we're trying to do. That there is synergy here, and it is in that synergy is really about the future. It is really about how we begin to understand and manage the world in which we live. And so we're looking forward to a deep collaboration with you, and also with your permission to figure out how we translate your work so that the more general American public has access to it as they make decisions. So I really want to thank you for that, taking the time with us this afternoon.
Yeah, thanks for the invitation to be here. It's been a splendid conversation. I really enjoyed it, and it was great to spend time with you all.
Great. For those who are staying on with me for a minute, I just want to say, because it's really important for you to understand a little deeper what NMQF is about, which is we want to follow those natural laws and bring them into healthcare. Um, um, Diseases like lupus and cancer and diabetes and heart failure, rare diseases, um, all of them, I think we have the capability to address. But we want to make sure that each and every American has access to the medications and to the quality of life that I think we can afford each other. And that's really the challenge. And so I think the language that you're going to start to hear from NMQF is more future oriented. It's probably going to sometimes sound a little discordant in that we don't talk about things exactly in that way. But the key piece of it is really about orderliness, that our bodies operate in a orderly manner. And if we want to address those diseases that we all work on, particularly the patient advocate community and the legislators who want to take care of their constituents, there is a rule book, and we have to follow it. And we have to make sure that each and every individual, no matter who they are or what they look like or what they suffer from, have the best of us working to make sure that they get access to high quality care. It's a very different way of looking at the world. And also to Dr. Wong's point, that we have to do it in the context of managing the environment in which we collectively all live in. That the choices are really ours. One of the unique things about these physical laws, they end up giving us choices and allowing us to make decisions about our future. And we're choosing persistency. We're choosing sustainability. We're choosing to go into those marginalized communities and bring the logistics into them. Uh, that logistic is followed by orderliness. That is followed by a deep understanding of those physical laws. And we need everyone's help. We work in barbershops and beauty salons and places where we need to translate this information. And obviously, with a lot of challenges with social media and all the other things that where people have an opportunity to philosophize about what they think is so. But at the end of the day, we all have to follow the science, and insofar as our bodies are concerned, we have to follow it to a degree of accuracy that brings with it sustainability. So I hope this has been helpful to everyone, because this is the journey that NMQF is on, and the work that we're going to try to pursue. So I want to thank you for taking the time, and look forward to a continued conversation with you. Thanks a lot.